Many of the applications of integration come down to integrating a rate, and that's a natural situation that occurs in a lot of data that people might come across. So, for example, I've drawn in advance a rate situation. So I've got a velocity v, and that's given in miles per hour. Um, Typically, if you're doing any kind of lab work, you're going to have some convenient unit of measurement for one aspect, basically for the variable quantity. And so if it's a car, you'd use miles per hour. And I've got time in seconds. And so there's a gotcha there that we're going to have to talk about. But that's the situation. And so what we have here is a graph that says that at any particular time, since the clock was started, you have the velocity of whatever object it is that you're talking about given by the height of this graph. So the first thing to notice here is that the distance traveled is the integral of the velocity. And this follows kind of from this general rule that if you have something that's expressed by a multiplication, but now one of the things varies, then you find that the multiplication becomes integration. And the reason is the definition of integration. And so what we have here is we're going to subdivide the interval. So I've got from 0 to 30, I've got half a minute's worth of stuff. You subdivide the interval, and then you pick a sample in each interval. And let's just look at one sample. And so the subdivision is, in this case, we'll just say that the base is delta t so that you can be general about it. And then you sample. So in the interval number I, you get some sample f sub I, and then you multiply. So this is the integration process. And so these kind of come together as f sub I. I'm sorry, I said f, and I really should have said v. So we'll call that v sub I times delta t. And now what you get here is that in each subdivision, the term of the sum is the rate times the time. Well, that's the distance. Distance equals rate times time. And so when you start to put these into the picture, so here I'm drawing f sub 2. I'm sorry, v sub 2. I don't know why I'm stuck on f. So what you're going to get is, here's one subdivision, and there's the sample, and you get the area of a rectangle. So that's this rectangle whose top is green, and that's approximately the distance traveled. So that's over one subinterval. So now you add those up. You know, in the first second you go this far, the second second you go this far, the third second you go this far. And so that gives you that sum, the sum part of the integration process gives you the approximation of the distance traveled, and then when you take the limit, you get the exact distance traveled. And so, so if the distance is s, then you get the following situation: if the time interval is from A to B, then the distance traveled is the difference between where you ended up and where you started, and you get that by integrating the velocity. So there are a lot of things that come up in various applications that are rates, and you integrate the rate to get the total change. So this is pretty much the fundamental theorem of calculus, but with a much more practical aspect to it. So anything that's given as a rate is integrated to get the total change. So rate of change integrates to total change. And so that's the situation. Now, with this particular kind of problem, what you're seeing here is, we'll go back to this picture again, the area of this rectangle is approximately the distance traveled. The area of that rectangle is the sample v sub I times the base delta t. That's the area. And that was also the approximate distance traveled. So what you're seeing here is, with the area interpretation of the integral, this is the area under the curve for v. So that works especially well if v is positive. So that's the area under v. V for velocity. So in a situation like this, what you can do is you can estimate the integral by estimating the area, and you can estimate the area by counting how many squares there are under the graph of v, and that will give you a good idea of the actual distance traveled. So distance traveled between time A and time B is the integral from A to B of the velocity, and that's the area. And you can get at the area, if you have a nice graph like this, by counting squares. It's not that easy. I mean, counting squares is easy. One of the things that you can do is, typically the velocity graph is cutting across the squares, not horizontally. Of course, it's never vertical. So the velocity graph cuts across the squares, and you can say, well, I got about half of one here and about half of one there, and so forth and so on. And so you have to count the squares carefully, but that's what happens. The gotcha is that the area of the square, that's what you're counting the areas under each little piece. The area of the square is a little bit more difficult to calculate than it would appear at first. So you might just say, oh yeah, each of these squares is 1, and that's wrong. Each of these squares is, the way I've drawn it, the base of any one of these squares is 2.5 seconds. I'll do this one up here. So based on the grid that I've drawn, it was 5 seconds for 2 squares, so 2.5. So I'll just say 2.5 seconds. And if you look at the vertical scale, that's 5 miles an hour. So the height of one of these squares is 5 miles per hour. And so you might be tempted to say, oh, 5 times 2.5, that's 12.5. So each square represents traveling 12.5 feet. But that's wrong, because this unit is in miles per hour, and this unit is in seconds. And the distance that you're looking for is in feet. So you also have to do a unit conversion to getting feet per second, FPS, rather than miles per hour. So let's take a kind of sidebar approach here and look at the unit conversion. So one statute mile is 5,280 feet by statute. It's a statute. A nautical mile is about 6,076 feet, and that's based on an actual measurement of the Earth. But we'll stick to statute miles for right now. So 5,280 feet, and so to convert from miles per hour to feet per hour, you would multiply by 5,280. And if you want to convert that to minutes, now you would divide by 60, because there are 60 minutes in an hour. And if you want to convert that to seconds, you would divide by 60 again, because there are 60 seconds in an hour. So 1 mile per hour Man, I can never remember this. I'm going to tell you what I can remember. But it is, it's a fraction, 5,280 on top and 3,600 on the bottom. That 3,600 is 60 times 60. And that is, oh, just peachy. I guess I better find a calculator someplace or a slide rule or something. Yeah, I don't have a slide rule. I'm going to have to use some electrons. And we can just calculate 5,280 divided by 3,600 is 1.47 approximately feet per second. FPS for feet per second. So there's the calculation I did. It's the unit conversion. And let me just kind of double check something here. That's not what I can remember. What I can remember is 60 miles per hour is 88 feet per second. And what's happened there is you've got a conversion that's gone on. 60 miles per hour is now the fraction is 60 times 5,280 over 1. And if you want to convert that to minutes now, you have to divide that. So that's feet per hour, excuse me. You want to convert to minutes, you have to divide that by 60. Now you notice I didn't multiply this out. I said it was 60 times 5,280 because you always wait before you multiply things out. To convert from per hour to per minute, there are 60 minutes in an hour. So this is still a fraction. The top is 60 times 5,280 and the bottom is 60. And this is now feet per minute. And the 60s cancel. That's why I didn't multiply it out, because you're always going to get some kind of cancellation. In a real world problem, there's always some kind of cancellation. And so we'll cancel out the 60s, and now we want to convert to per second. Well, 1 second is 1/60th of a minute, so this is 5,280 divided by 60 feet per second. And that's 88. So 60 miles per hour is 88 feet per second, and that makes your conversion quite precise. I just find that easier to remember, and so 30 miles an hour is 44 feet per second, and 20 miles an hour is about 30 feet per second, a little bit less, and so you've got this one conversion is the one I find easiest to remember. Or else you can go through this calculation every time. Okay. So that means that each grid square, let me draw one a little bit bigger. Each grid square, which was the base corresponded to 2.5 seconds, and the height corresponded to 5 miles per hour. Well, 5 miles per hour is, let's see, I'll take 88 and I'll divide that by 60. So there's my 1 mile per hour expressed in feet per second times 5. So we're looking at 7.33. Excuse me, my dog just came here. Yes, Sammy, it's okay. Okay. She doesn't do a lot of math, so, but I guess she likes to hear me talk about it. Anyway, so the 5 miles per hour height on this little box corresponds to 7.33 feet per second. And so the area of the box corresponds to, I'm sorry, I need to do some more multiplication. I'm getting this for the area of each box, 18.3 or something. So each box under the velocity curve represents 18.3 feet of travel. Now it's weird because this is an area, that's a distance, that's a speed, that's a who knows what else it could be. But so you got to be careful how you say this. Each box corresponds to 18.3 feet of travel. So the only thing that's left over is to count the boxes, and this is going to be very boring because I didn't do it in advance, and you can't do it in advance. And so I'm just going to start counting boxes, and I'll put a little dot in each one as I count it. So, and what I'm going to do here is, let me illustrate it with a slightly bigger picture. Is if you have a situation like this, where the curve is cutting the boxes. I get about half a box here and about half a box here. So I'll shade in what I'm talking about. So between the two, I've got about a box. And so this is a judgment call. If you wanted to be super careful about it, then you could be much more precise. But we've got limited time. So anyway, I'm getting 1, 2, 3, 4, 5, 6, and I'm going to call that a seventh because of there's a little bit more here and there's a little bit less there. So I'm up to 7, 8, 9, 10, 11. That's pretty clear. 12, 13, 14, 15, 16, 17. I've picked one out further up to finish that off at 17. 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Isn't this your nightmare of a math class? Just some guy counting. 35, 36, 37, 38, 39, 40. I'm skipping the top one there. 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53. I'll call that 54. 55, 56, 57, 58, 59, 60, 61, 62, 63, 64, 65, 66. So I've hit 66 boxes, and I got a couple of unmarked ones, and I'll change colors for those. So I'm going to say between this one and this one, this is at the upper right, that's one box. So what was that? Now we're up to 67. And then I've got between this one and this one, kind of in the middle here, we're up to 68. And then, yeah, this one and this one, kind of looking on the left, we're up to 69 boxes. 69 boxes. So that corresponds to 1,265 feet. Now, that's what I'm saying the integral is. Another way to look at this, and we'll be more formal about this after we've done the fundamental theorem of calculus, is you can say, this height here kind of represents the average speed, sometimes below, sometimes above. This is definitely just an eyeball estimate. And so I'm going to say 25 miles an hour for half a minute. So this is just a check to see if it's reasonable. So 25 miles per hour for half a minute. Well, 25 miles per hour is 25 times 1.47. So that's 37 feet per minute. I'm not sure where I'm going with this. So 25 miles per hour for half a minute is that's half a minute is 1/20th of an hour. So we're looking at 25 over 120 times 5,280, and that's let's find out. 25 times 5,280 divided by 120. That comes out to be 1,100. So if you just did just subdivide into one thing, you might get an estimate of around 1100. And if you're more careful, you'll get an estimate of 1265. So they're in the same ballpark. But the best answer that you can do by counting boxes is to count and say, oh, that was about 69 boxes. Each box represents 18.3 feet, and so 69 times 18.3 is 1,265. And so that's the distance traveled. And that's also the area under this curve if you use consistent units.